the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is yet another video for students in linear algebra who are going through eigenvalues and eigenvectors, specifically diagonalizing matrices. I actually broke up my previous video on the diagonalization theorem into two chunks because it was so long. So this is actually the second half of that video. Sorry if the voice for today sounds different than the voice I recorded yesterday. It's the same person, just a different time of day. Let's diagonalize this matrix A. What we know now is if it is diagonalizable, then all I need to do is find its eigenvectors. I'm just letting you know, it's not a unique diagonalization. A lot of people think, oh, this means, that last theorem means that there's a unique matrix for D. And that's not true because you can actually order those eigenvalues any which way you want as long as you order your eigenvectors accordingly. But let's go ahead and work with this bad boy right here. We now know to find the eigenvalues, we'll build the characteristic equation. And we'll expand about any row or column we choose, and you better believe it, I'm going to expand about column 2. Just one more determinant to go. And as I mentioned in my video on the characteristic equation, if you already have it pre-factored like this, do not multiply things out, please. You can multiply both sides by a -1 to get rid of that silly negative in there. Always remember to check your arithmetic. There is always a chance for ruining things through bad arithmetic. I do it all the time. And we find our eigenvalues are -6, 5, and -1. Now, honestly, they say diagonalize A, which basically means find a similar matrix to A that is a diagonal matrix. Now, that matrix A is similar to a lot of matrices. But as far as diagonal matrices, well, that's a very small number. And one such diagonal matrix that is similar to is this guy right here. Remember, the eigenvalues will be listed as the diagonal entries of D. Now, did I have to choose that specific order? No. But the underlying matrix P that gets me to this D will change. In this case, if I really want to find the matrix P used for the similarity transformation, I'd have to find the associated eigenvectors. Now, there's always a little bit of a frustration for me when somebody says diagonalize a matrix. What I hear is find the matrix that is similar to A but is diagonal, and so I have done so. However, for other computations, specifically powers of matrices, we do actually need to find out what P is. So part of diagonalizing a matrix, unfortunately, is finding the eigenvectors for those eigenvalues. So let's go ahead and do that. I'll do that work in blue. So the work in black here is basically us finding the diagonal matrix that's similar to A. But now we have to find P from that similarity transformation. Remember, P is just going to be a matrix full of eigenvectors that are associated with these eigenvalues. In fact, I'm going to write that here. There we go. P is a matrix whose columns are the eigenvectors associated with the respective eigenvalues shown in the matrix D. Going through one by one and finding those eigenvectors. If lambda is equal to -6, we'll take the matrix A and subtract a -6 from its main diagonal. So 4 minus a -6 is, well, 4 plus 6 or 10. -6 minus a -6 is 0, and 0 minus a -6 is 6. That's how we got there. And now we'll go ahead and do row reduction techniques. And we get down to this guy right here. Notice x sub 2 is a free variable in this situation. And we arrive at this parametric vector solution to that homogeneous equation. And that tells us the eigenvector associated with lambda equals -6 is the vector 0, 1, 0. To use language that we've developed recently, we would say that the basis for the eigenspace corresponding to lambda equals -6 is this vector 0, 1, 0. So now that I know that eigenvector, I'm going to go back up to this matrix P right here. I'm going to erase this first column and replace it with 0, 1, 0 because that column is associated with the first column of D. I'm going to do the same thing for lambda equals 5. I'll use a different ink for that. Now, one thing I want to mention here, there's really no need for me to write this augmentation column right here. So if you do not, that's perfectly fine. You're actually still solving the related homogeneous equation. It's just that you know that augmentation column is always 0, but I'm going to continually write it. Again, not a necessity for you, but I'm going to do it. This one's a little more interesting. We see that x1 is equal to x3, negative 11x2 is equal to positive 3x3, and x sub 3 is free. And here is another great example of allowing our parameter x sub 3 to be something that kills off fractions. So I'm going to let x sub 3 equal 11 so that the eigenvector corresponding to lambda equals 5 is 11, negative 3, 11. That's a basis for the eigenspace corresponding to lambda equals 5. And replacing our second column of P up above with 11, negative 3, 11. We're filling out that matrix really nicely. We have this last eigenvector to find associated with lambda equals negative 1. Using a different ink for that, we get here. Now let's go ahead and just clean this up. And you'll see that I actually used some fractional magic there just to make the math a little bit cleaner. And we see here that x sub 1 is a negative 1/5 x sub 3, a negative 5x2 is a positive 9/5 x sub 3, and x sub 3 is free. And we get down to that vector right there. Obviously a pretty decent choice for x sub 3 in this case would be 25. And so we find that the eigenvector associated with lambda equals negative 1 is negative 5, negative 9, 25. Again, depending on your choice of weights for x sub 3, your eigenvector might look slightly different. Not that big of a deal. So we're going to go ahead and replace that up here. And there we have it. We have diagonalized A. We know what D is. We know what P is for our similarity transformation. I will leave it to you to double check that A times P is equal to P times D. You're more than welcome to do that. I will promise you they are the same. But it is a really good way to check your work, especially on an exam or something like that. So just letting you know, if you want to check your work here, let's say you're working on an exam or a quiz or something, and you have the time, well, you know you've done the right work if A times P is equal to P times D. Computing that out, you will find those two matrices are exactly the same. Now let's talk about a theorem that seems like I've mentioned before, but I haven't actually mentioned at all. Now what I did mention with the diagonalization theorem is that if you have an n by n matrix and you have n linearly independent eigenvectors, then A is diagonalizable. But we never mentioned anything about eigenvalues. But this theorem is going to fix that. A square matrix with n distinct eigenvalues is diagonalizable. Now, the reason why this specific theorem is not in the diagonalization theorem is that this is not an if and only if. In other words, if you have a diagonalizable matrix, it's not necessarily the case that you have n distinct eigenvalues. However, if you do have n distinct eigenvalues, you do have a diagonalizable matrix. So let's go through the proof of this. Let A be a square matrix with n distinct eigenvalues, lambda 1 through lambda n, and suppose the corresponding eigenvectors for these eigenvalues are v1 through vn. Now we have a theorem from the past that tells us eigenvectors corresponding to distinct eigenvalues form a linearly independent set. And that's what I've written here. So those eigenvectors that correspond to these distinct eigenvalues form a linearly independent set. Hence, that set of vectors is linearly independent, and therefore A must be diagonalizable by the diagonalization theorem. That's a pretty fast proof, honestly. It'd take longer if I was handwriting it out, but generally speaking, I don't need to handwrite all that stuff out. It's a little bit cleaner actually just doing it this way. So now you know, n eigenvectors that are linearly independent means your matrix is diagonalizable. N distinct eigenvalues means your matrix is diagonalizable. Your matrix being diagonalizable means you have n linearly independent eigenvectors. However, A being diagonalizable does not mean that your eigenvalues need to be distinct. And here is a perfect example. This matrix is diagonalizable. Why? Multiply it by the identity matrix on both the left and the right, and you get a diagonal matrix. So this can be transformed via similarity transformation into a diagonal matrix, which it actually is. Its eigenvalues are 3, -1, -1. Notice they're not all distinct eigenvalues. This matrix is diagonalizable, yet it does not have distinct eigenvalues. So there you go. There's a good counter example. Just be very careful with that. So again, distinct eigenvalues implies diagonalizable, but the converse is not true. Rather than following that up with an example, because all I would be doing is basically doing another diagonalize example, and there's no point. Once you know how to diagonalize, there's not a big deal about doing it over and over again. Instead, let's play with some powers. And the theorem we're going to need for that is this guy right here. If A is diagonalizable, then A to the nth power is P times D to the nth power times P inverse, where, by the way, that P comes from the relation A is equal to P D P inverse, or in other words, P inverse AP is equal to D. So if A is diagonalizable, then there exists a matrix P that's invertible such that P inverse AP is equal to D. Multiplying both sides on the left by P and on the right by P inverse, we get to this relation. And we're being told that if you want to take A and raise it to the 1000th power, well, rather than multiplying A by itself 1,000 times, if you can find the diagonalization of A, then possibly it's easier to raise A to the 1000th power. And it actually is, because D to the 1000th power, trust me, is much easier than A to the 1000th power. And we'll see why in a moment. But let's go ahead and prove this theorem very quickly. Suppose we have a matrix A that's diagonalizable. Then there must exist an invertible matrix P such that, well, as we said above, P inverse AP is equal to D. Therefore, A is equal to PD P inverse. Hence, and now what we're going to do is take a look at A to an extreme power, specifically the nth power. Well, that's going to be this right here. Since A is PD P inverse, A to the nth is PD P inverse to the nth. Which, by the way, if you were to expand that right-hand side out, it would actually become this guy right here. This is an M of those products. So it's PD P inverse times itself M times. But you're more than welcome to associate the multiplications differently. Instead of PD P inverse, PD P inverse, PD P inverse, you could write it as P times D and then P inverse P, D, P inverse P, D, P inverse P, and at the very end, you'll have a D, P inverse. Of course, all of those P inverse P's are the identity matrix, and so it compresses down significantly to this. And remember, we had M of those D's, so that will be P, D to the nth, P inverse. And that is the entire proof of that theorem. It's actually not too terrible. It's a very nice theorem to know and to prove. So let's go ahead and use that theorem on this matrix right here. Find A to the 10th, given that A is equal to 4, 3, -2, -3. Now you may not recognize it because it's been a little bit, but this guy right here, we were told to find the eigenvalues and eigenvectors of this matrix. At the time, we had no clue that what we were actually doing was finding P and D, but that's exactly what we did. So I'll go ahead and copy over the eigenvectors and eigenvalues and place them appropriately in P and D. So I went ahead and copied down everything that we needed. This P right here, that is the matrix of eigenvectors. This is D off to the right here, and it is the matrix of eigenvalues that correspond to those eigenvectors, and it's the diagonal matrix. And what we're going to do is quickly compute out P inverse. And I'll even move that -1/5 out front. Now remember what we were faced with. We wanted to raise this matrix to the 10th power. That would be 10 matrix multiplications that we'd have to do. However, there's a cool little fact about diagonal matrices and their powers. And since I can't remember if I proved it for you, I'll at least showcase it because the proof is done through induction and I just don't want to do a long induction proof. But at least I'll say, well, what if our diagonal matrix was this guy right here and we wanted to square it? That's what the action would be. But when you start multiplying things out, you get to this right here. And that pattern actually will continue for all powers and all sizes of square matrices. So essentially what I'm telling you is, if you want to take the 10th power of this matrix, it's just going to raise the diagonal elements to their 10th powers. This is only true for diagonal matrices, so please do not assume this is true for all matrices. It is not, but it is true for diagonal matrices, so let's go ahead and do that. Notice I didn't bother actually applying the powers on there. 2 to the 10th I'm very familiar with, that's 1024, but 3 to the 10th, that's just a crapshoot for me, so I'm not going to bother with it. But let's go ahead and multiply things out. Now, that is a bit awful and large, but still, it beats multiplying a by itself 10 times. So I hope you could see the usefulness of diagonalization for powers of matrices. It really does reduce the amount of computational time because you're taking advantage of the fact that a diagonal matrix raised to the nth power is the diagonal matrix where the entries are raised to the nth power. It's a really, really nice use of diagonalization. All right, that does it for this video. And in the next video, we'll round out this topic of diagonalization by revisiting something called eigenbases. I'll see you there. Have a great day. Be a wonderful human being.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.